Section 2.4, the precise definition of a limit. Precise definition of a limit. So what we need to do here, first we need to recall something from algebra. Recall of the absolute value of x less than or equal a positive number a. This is a positive number. Then x is between from negative a to a. The absolute value, also the absolute value of x is less than a, same thing, x between negative a and a. So, for example, if I want to solve the absolute value of x minus 3 less than 7, the way this is done, x minus 3 is less than 7 and bigger than its opposite. We can add 3 to all sides, becomes negative 4 less than x less than 10. We introduce now some new symbols. This small symbol called small delta, a Greek letter, and this is called epsilon. We're going to use them in this section. We start by saying let f of x be a function, defined on an interval containing x equals a except possibly at x equals a. We say the limit of f of x as x approaches a equals L if for every epsilon bigger than 0 we find a number delta bigger than 0 so that the absolute value of x minus a is absolute value of that less than epsilon means, delta implies, this symbol means implies, absolute value of x minus L is less than epsilon. So that's really the precise definition of the limit. We said the limit as x approaches a of f of x equals L if for every epsilon bigger than 0 we find a number delta, very small number delta bigger than 0, so that if the difference between x and a is less than delta, then the difference between f of x and L is less than epsilon. Well, what does this mean here? If I want to break it, jump the absolute value, this is bigger, less than delta and bigger than negative delta. If you add a to all sides, you get this. Let's keep this in mind for now. Let's do the same thing for this one. Add L to all sides. And let's keep this as well. So this is the function f, this is a as x approaches a, say the limit is L. So what's happening is that if when we pick a point here, we're trying to approach a from the right side, that would be the corresponding y value. When approach again, that's the corresponding y value. Approach again, this is the y value. If you pick a point here, so what's happening here is that x, when x between a minus delta and a plus delta, this point here is a plus delta, this point here is a minus delta, and this point, it goes all the way to this one. This is the epsilon plus L. This is the epsilon minus L, or L minus epsilon. That's what graphically it means. Now to apply this to an example, to see how do you work out problems, let's say we are asked to prove the limit of 2x plus 1 as x approaches 5 is 11. So this looks like the limit as x approaches a of the function f of x is L. How is this done? For every epsilon bigger than 0, we find, or we can find, a delta bigger than 0, so that x minus a less than delta implies f of x minus L less than epsilon. So that's what the main definition. How are we going to use this? Well, let's see. F of x here is the 2x plus 11. L is 11 and a is 5. So a is 5. F of x is 2x plus 11, plus 1. And L is 11. So what we need to prove here? We need to prove that when absolute value of x minus 5 less than delta implies f of x, which is 2x plus 1 minus 11, is less than epsilon. How do you do that? Well, let's see. We write first, choose delta to be something epsilon, which we'll come back to it in a minute. Leave it blank like this. And let's start with this one. So the 2x plus 1 minus 11 equals 2x minus 10. And we can factor the 2 out, which is x minus 5. But what do we know about x minus 5 absolute value? We know it's less than delta, so it's 2 times delta. But remember, I want to get to epsilon, so this can only be done equals if I take delta to be epsilon over 2. So if you put epsilon over 2, these cancel, and that would give us epsilon. And that's what we're looking for. So what we just did, we proved that when absolute value of x minus 5 less than delta, then the 2x plus 1 minus 11 is less than epsilon. So that tells us that the limit of 2x plus 1 as x approaches 5 is 11. Another one, prove that the limit of 3x minus 5 as x approaches 3 equals 4. How do we do so? We start, what we say, a here is 3. The function f of x is 3x minus 5, and L is 4. We need to prove for every epsilon bigger than 0, we can find delta bigger than 0, so that x minus 3 less than delta implies 3x minus 5 minus 4 is less than epsilon. Again, same process. We choose delta equals something in terms of epsilon, which we'll come back to it in a minute, and start with that big parentheses, absolute value, 3x minus 5 minus 4 equals 3x minus 9. Factor a 3 out. But the absolute value of x minus 3 is less than delta. But what is delta? Delta should be epsilon over 3. So you put epsilon over 3 there. And that would give us what we need. One other example, prove that the limit of 3 plus 5x over 2 as x approaches 1 is 4. We take a1, f of x equals 3 plus 5x over 2, and L equals 4. what we need to do, we need to prove for epsilon bigger than 0, there is a delta bigger than 0, so that absolute value of x minus 1 less than delta implies 3 plus 5x over 2 minus 4 is less than epsilon. So again, we choose delta equals something in terms of epsilon, which we'll come back to it in a minute. We start with the absolute value 1, this one. What can we do here? We can combine the fractions by taking the LCD 2. Then on the top we get 5x minus 5 over 2. Take a 5 out and keep the 2 out. X minus 1. Now we know that this is less than delta. So in order for this to work out, delta should be 2 over 5 epsilon. So this way I get epsilon. So delta should be 2 over 5 epsilon. That's how things are done. Other examples on this. If we have a function f of x, a graph is given. (2.8), 3.3. Find a number delta such that if the absolute value of x minus 3 less than delta implies f of x minus 2 less than 0.3. Assume the equation of f of x is given. If you look at this given stuff, this is epsilon, this is L, this is A. So A is 3, so 3 is here. So this is A plus epsilon, and this is A minus epsilon. What is delta 1? Which one works? Is it the 3 minus, is it this or this? Because if you look back at the main graph, we had A plus delta or A minus delta. So epsilon doesn't work out here. So A plus delta and A minus delta. A plus delta, A minus delta. Well, let's see. If I go, how do I know which one is delta? So let's call them delta 1 and delta 2. Delta 1 is the distance between 3 and 3.3. That gives us 0.3. This is between 3 and 2.8. 0.2. Delta would be the smallest, the minimum of the two deltas, delta 1 and delta 2, which is 0.2. That's delta. That's what they ask us to find. So delta would be which one is smaller. The smaller or the closer to A, the better. The closer the A, the better. The smaller the delta, the better. Another example. This is y equals x squared. Find the number delta such that if the absolute value of x minus 1 less than delta implies x squared minus 1 less than 1/2. to start with something like this, this is A is 1, so A is 1. This is L, this is epsilon. So epsilon is 1/2, 0.5. So if you project it up, the y value is 1 because the function is x squared. Remember, we need delta. Delta is on the x-axis. What we do is, this is L. If I go L plus epsilon, which is 1.5, projected this way and down, we need to find out what that is. And if you go down L minus epsilon, projected this way, what is this? To do so, we need to find the x value that corresponds to y equals 1.5. Y equals 1.5, so 1.5 equals x squared, and 0.5 equals x squared. So if I want to find the x value, is the square root of that, x value square root of that. So x is about 1.2247, and here is about 0.7071. So this value goes in here, and this value goes in there. So we need to find delta now. What is delta? We have delta 1 is the distance between A, which is 1, minus the 1.2247, and that gives me 0.2247. Delta 2 is 1 minus 0.7071, which is 0.2929. So delta would be the minimum of the two deltas, delta 1 and delta 2, which is 0.2247. That's how we find deltas and work with deltas and epsilon graphically.